Hey everybody, this is Rajesh. I have Sandhya joining me today, and we're really excited to show and take you guys through the journey that we went through at Asurion in measuring, monitoring, and surfacing the data quality metrics. So before we go into the actual content, a few customary slides talking about who Asurion is. Asurion is a tech care company, so we sell and offer protection plans on anything that has a power button. So if you're buying any phones from AT&T or Verizon, most likely the protection plan is coming from Asurion, and so is anything that you click and buy on Amazon. You see the little checkbox that says like buy a protection plan, that's coming from Asurion. We service that. And we care for people and their tech wherever, whenever, and however. And we have over 300 million subscribers all over the world. And of course, we operate on a global scale, and we are operating in 17 different countries, and we have over 700 retail stores all across the world. And we also have 11,000 plus experts, and they're available virtually in stores and also on the road. To take care of, obviously 88% of the US population is covered through these 11,000 experts. And over the period of time, we have built long-term partnerships with a lot of these clients that you're seeing on the slides. Now that that's out of the way, back to the actual content. What is data quality, right? In very simple English, it's a measure of how well the data meets the requirements and expectations of its intended use, okay? So what amplifies the need for data quality? Why are we why should we pay attention to data quality is the question, right? So this is a simple example of our data platform, what we do on a day-to-day basis on our data platform. We run over 10,000 plus jobs on a daily basis, and those 10,000 plus jobs go over 100,000 version changes. That means each transaction is a version change. In other words, we are touching the tables over 100,000 times in a day. So each time you touch the table is a chance to make a mistake, right? So irrespective of taking the data through these many changes and processing over 20 billion records every day, you still have to give the business accurate data, because at the end of the day, no matter how fast or how sophisticated is your data platform, it doesn't matter, because if the data is not in usable state, it's useless. So I would argue data quality is at the heart of actually the most important thing for your entire data platform to be successful. So having said that, honestly, like we have data quality issues irrespective of all of the cutting edge technologies. And a simple look back into what happened like in the last 90 days is like we caught over 80 data quality issues, and we spent time in fixing this. So all of that time that you are spending in fixing these data quality issues is something that you can automate and then move away to using an automated framework. So over the period, as we started our journey like 8 years ago, and then we went through a lot of series of changes, we learned our lessons, and we added all of that and condensed that into these 6 types of data quality issues. So accuracy is all about the completeness and precision of the data, like for which we can use custom code configs. Like you can actually start writing SQLs, and that's where 90% of the data teams actually start by writing SQLs, and then they compare like source system values with the target system values, and they write business rules and everything, and that's how they validate. That's where everybody starts, and that's our framework for custom code config. We have built a framework where you can just plug in SQLs and it orchestrates on schedule and then spits out the results. Simple and straightforward. The second one is completeness. It's all about you have X number of elements required to make a decision, but only X minus 1 are being published or something is missing. So that's all about completeness. And also if the data is not well defined, it's not usable because it is not discoverable. So the metadata is also playing a role in this and making it complete. So that is all about completeness. So we use data profiling softwares or open source frameworks like AWS DQ for those things. The uniqueness is straightforward. It's all about duplicates in the data. So if you have duplicates, your numbers don't add up. So that's not good, right? So data profiling can catch uniqueness issues. The next one is timeliness. No matter how well you organize all of your data, if the data is not arriving, or maybe it is supposed to arrive today, but it never arrived, That means the job never ran and the data never loaded. Even that needs to be caught. So the only or easiest way to catch those are using anomaly detection frameworks. So we use up-to-date data, metadata, and we use anomaly detection frameworks to catch the timeliness issues. And the last two, validity and integrity, these are the most complex ones. And on the right hand side, you see the complexity scale. So the first three are very easy to implement, easy to medium to in terms of complexity to implement. The last one is where we spent significant amount of time in innovating the last pieces of data quality issues. So no matter how you choose to catch your data quality issues by writing business rules or by writing SQL or by doing data profiling, there is a last piece that is missing, and that is all about structural integrity. So structural integrity is nothing but it defines the relationships between a record. Like if you have a record and a record is made up of 15 different attributes, there is always a relationship between these attributes. So an example, like if you have a claim submitted by a user, the survey about the claim doesn't go until the claim is complete, right? And you won't get paid or you don't charge the customer until you make the shipment or the shipment is delivered or something like this. So there is always an inherent relationship between those attributes inside a record, and that is all about the structural integrity. Minor variations in those relationships can also impact your data quality, and that is something that you can detect using structural integrity checks. And that is actually really complex to implement, and that is where machine learning can help us. So I'll hand it over to Sandhya. She's going to take over us through how we actually implemented it and how, and she's going to use a very good analogy to help you understand how structural integrity can help you catch data quality.
So before we go into the structural integrity and at a high level, I just want to do a quick walkover on the number of validations that we're doing at the platform level as of today using the 4 frameworks that Rajesh has mentioned in the previous slide. Is using the custom code SQL, we have 2000 plus SQLs written by the individual data product teams, which they think are the core validations that they want to do on a daily basis, on a schedule or an event based. So they have all that defined in our database. So we do the 2000 plus checks every day on an average, and along with that, in the data platform, we have thousands of data assets, and we did do the data profiling of more than 200,000 columns on a daily basis. And coming to the anomaly detection, using anomaly detection framework, we scan like more than 15,000 data sets every day. And now coming to the structural integrity, it's a new framework that we have in place in the platform, and as of today, we have 200 plus data sets being profiled using that structural integrity. At high level, before we jump into the structural integrity, I just want to give a high level overview of how we are doing the data profiling and the anomalies in the data lake level. So for data profiling, we are leveraging AWS DQ, which enable us to systematically ensure data quality and profiling of those data at the platform level. Using this, we automated the complete profiling process for each and every table at the data lake level. And this strengthened our confidence in our data lake's reliability and trustworthiness. And coming to the anomaly detection, we're using it for the volume and refresh stat related checks. So using the machine learning and the statistical models, we are feeding in the historical stats of the refresh related information of all these previous data from all our data lake tables. We are using the trend and seasonality of the data to identify the refresh delays and the volume related anomalies in the platform. So getting into the structural integrity. So this is the core topic for today, and how are we solving the structural integrity issues at this scale? So the solution we have is autoencoders. Autoencoder is a type of neural network which learns to which is designed for unsupervised learning. It learns to represent the data into a compact representation and they reconstruct this data back to the original form. During this process, it learns all the key features and the relationships in the data. For this ability, it is often used for data compression, feature learning, and anomaly detection. Just like any other machine learning model, autoencoder need to be trained for inference. The image we see here is a simple autoencoder architecture which has an input layer, encoder, decoder and an output layer. At the time of training, the input data is fed to the encoder, which is nothing but a series of mathematical operations, also called as activation functions, which encodes the data to a low dimensional latent space. And the encoded data is fed to the decoder, which try to reconstruct the record back to the original form. During this process, it learns, at the end of the cycle, the model tries to compare the reconstructed record with the original record and calculate the loss in the data and feed it back to the network. So the network adjusts the model weights and biases according with a goal to minimize the reconstruction loss. It repeats this process iteratively until the model learns to effectively reconstruct this data using the encoding and decoding process. So when we have this model ready, it knows how a good quality data should look like, because the input is trained based on the good quality, and that's the key of this. Like, we will not feed in the expected bad quality records to the model. It's purely trained on the good quality data. Moving on to the inference, the architecture remains the same as how we do at the time of training. The input data is fed to the autoencoder, and the autoencoder take it to the encoder, and the encoder try to encode the data, and the decoder try to reconstruct the record back to the original form. So the process is same exactly like how it is trained. But here, if the input data that we are feeding to the model is of good quality, which means the relationship in the data is in accordance to what it was trained, then the model knows how to extract the meaningful key features from this input data set, and it then compresses the data to a low dimensional space, and the decoder would be able to reconstruct it back with a very minimal loss. If the input data quality is of bad, then the model struggles to extract all these meaningful features from the input data. It still try to encode the data, but the decoder struggle to reconstruct the record, and the reconstruction loss would be very high in this case. When we input the data set, there could be mix of good and bad quality records, but this autoencoder takes the data, or it does at the row level. So it knows if the record is at the bad quality, the reconstruction loss would be very high for that record, and when compared to the good quality records. We are using this ability of an autoencoder to detect the structural integrity issues at this scale. Let's look at a simple analogy to make it more clear. Is imagine we're feeding a good quality cat image to the model. So if we imagine that the low dimensional representation of this cat image is looking something similar to what we see on the right hand side, then when we feed hundreds of good quality cat images to the model learns that the eyes, ears, nose and mouth of the cat are the key features of the cat image, and also it understands the relationship, which is nothing but the position of each of these in accordance, based on all the pictures that it is fed with. So if we think that when it represents all this information to a low dimensional space, imagine it looks something similar to what we're seeing on the right hand side. So at the end of that model training, it knows how a good quality cat image should look like. But when we feed in a good quality cat image to it able to understand where the eyes, ears and nose, this position should be, and it will be able to able to encode it to a low dimensional space effectively, and the reconstruction loss in this case would be very low. But when we feed in a very bad quality cat image to the model, imagine like here we expect the model expect the ear to be on the top of the head, whereas in the picture that we feed in, it's next to the cheek. The model, ideally we expect the model to encode it to somewhere close to what we're seeing on the right hand side. But what happens is, it never saw this relationship with the hundreds of images that we trained at the time of training. So it tried to reconstruct or try to represent this in the low dimensional way somewhere close to what it learned at the time of training, like by taking this ear and putting it in the top of the head. So when we compare the reconstruction loss for this record, like the right hand side is what we are expecting, and the left hand side is what it actually reconstructed out of that bad quality image. When we calculate the reconstruction loss in this case, it is very high compared to the reconstruction loss we saw in the good quality image. So with that helps in when we are feeding in 10 good quality cat images along with one bad quality cat image, that image will stand out as an outlier even though it's coming with a group of good quality images. Now, how does this applies to the tabular data, right? So we here took an example of an incident data. So we see that the top section is of good quality incident data, where each incident is associated with a status like in progress, open, resolved, or escalated. And every incident record has a created date. So definitely there should be a created date across for every record in here. And if the incident is in resolved state, then the resolved date should be not null. And if it's escalated, then the escalated date should be not null. If the model is trained with this good quality data set, it knows that all its relationship, even something that I haven't mentioned here, it has that ability to learn every relationship between each of these features, between these columns, and it is ready for inference with this good quality data set. Imagine we're feeding a bad quality data set that is at the bottom of the screen, which is the first top 3 rows are of good quality, which are in line to how it is trained. But the bottom 2 rows, the 4th record, which has the incident created date is null, and the 5th record where the incident is in resolved state, but the resolved date is not null and the created date is not null. So these 2 records are not in accordance to what it learned at the time of training. So the reconstruction, it won't be able to reconstruct this record properly, and the reconstruction error for this record would be very high and which will stand out as an outlier. And just like the example I gave in the cat images, when we are feeding in thousands of these tabular data records to the model, it will be able to isolate this good versus the bad records using this model. Let's get into details of how we are implementing this. So the first step here is identifying the data set that need to be trained, and basically the good quality data. Like data is available in our data lakes, but the thing is we need a labeled good quality data given by the SMEs of that data set. So once that is identified, then we need to identify the key features in that data set. I mean, a table might have hundreds of columns, but we are not interested to use all the 100 columns to train the model. If we can get down to what are the key features in that data set that defines the inherent structure of that record, if we can get down to that and if we feed directly those fields for this model, we do a pre-processing of the data so that the model understands how to take the data, because the data could be a string value or a numerical value or a date field or could be a money type. Whatever we need to bring it down to a numerical representation before we feeding into the model. So we do a pre-processing and then feed the data to the autoencoder model. So the model learns, what it does is it does a repetitive trials on this data until it learns how to encode this data properly and decode it back with a very minimal loss. Once the model is fully trained and once the model is ready, we offload the model weights and hyperparameters to a data store. It could be anything like an S3 or we use RDS. It could be anything depending on the data size and what we are training. It will be offloaded, and at this point, the model can be discarded. We can take it out from the memory, and to bring back the model again, everything is stored in the data store. So at the time of inference, since the plan is we want to put this model in the pipeline, as a part of the pipeline, right? So we train it once, and we can retrain it based on the volatility of the data. But when it is trained and when we want to use it in the pipeline, at the time of the process, based on the data set that's coming through, we load the model in the fly. We pick up the data that is stored in the RDS, and it takes less than a few seconds to load the model using the hyperparameters and the weights from the data store, and the model will be ready for the inference. And then we take a sample of the data set from the incoming pipeline and we feed into the model, and the model does exactly the same thing. It tries to encode and decode it, and it tries to calculate the reconstruction error. If the reconstruction loss is high, obviously we will make it as an anomaly. Here we do a sampling, like in the pipeline we might be getting millions of records, but we will do like, let's say 5% of the records for the first batch of anomaly for detecting the errors through this model, right? So if we see the ratio of the number of records that we are inputting to the model and the number of records that are set as an outliers, based on the ratio, we keep increasing our sampling size. And if the second sampling also results in like higher anomaly or higher reconstruction loss, then we will abort the pipeline and we see what's going wrong with it, so that we stop propagating the bad data to the downstream. So the same thing, even if the bad record comes with thousands of good quality data, we should be able to identify with this steps. What's the impact of this? We improved 2 times of the reduction of data quality issues in our platform. And also with this, we covered an automated detection and prevention of our data quality issues. And foremost, like we improved the trust in our enterprise data. And also we reduced the reprocessing cost, like whenever, like since we're doing a proactive check on the data rather than being reactive, we reduced our cost of reprocessing with the defective data. So how does this change our complete data quality evaluation? So as I said, we're doing a proactive versus reactive checks, like being reactive after data being loaded to the downstream and creating an incident. So this is more of a proactive measure so that we prevent flowing in the bad quality data to the downstream process. And as I said, this is a sampling. Like we don't do exhaustive, like we won't push everything that's coming through the pipeline to the model for detection, but we do a sampling like 5% first. And if we see anomaly, like the reconstruction loss, like high reconstruction loss with that set, then we increase the set and then we see until we are confident that it is a real issue in the pipeline. And then this structural integrity, as I said, we might have shown a very simple tabular data for identifying the issue, but this is very efficient in identifying something we haven't thought about. If we know what's the problem you are trying to look for, you can write a simple SQL to identify that issue and you can have some sort of scheduling or eventing to identify the issue. But if you don't know what you are expecting or what it is coming through the pipeline, it's hard to detect those issues. But this is very good in doing such things because it's intelligently learning those relationships based on all the features that we input, something that we haven't thought about, right? So that's why it's very great in that aspect. With this, so we're not saying that only this will solve all your data quality issues, but we need to, as we've shown, like we need to handle these data quality issues from all these directions, and all these frameworks collectively will solve your data quality issues in the big picture, in the data lake level. But with this structural integrity as an addition, in our case, it completes the data quality coverage in our platform. And that helps us to predict or be ready for unpredicted data quality issues in the future. That's it, and thank you.
Thanks for the presentation. This was really great. Do you feel like there is a semantic or the business context that might be missing? Because you might learn a rule that's encoded that machine might think that that's the right rule, but the business might say, yeah, you know what, that's right, but semantically. So do you have you thought about how to bring the business context?
Yeah, so what you can do is the key for this to work is actually to have like good quality data first identified. So we can actually choose to tag or identify and saying these are out of these million records, these 400,000 records are the good quality records, right? As long as you can identify the good quality, you can pick and choose the model's bias and say that this is what you need to be looking for. So if you, in your case, if out of those 400,000, only 300,000 are the true good quality records applying the business rules, but 100,000 are not actually falling into the business rules, you can choose to use only those 300,000. So that way you can control what the model can and cannot flag.
And also when you are picking up the features, which is nothing but the number of the columns in your data set. So you pick up only the columns that make sense to be part of that modeling, right? Like you eliminate all the unwanted fields in the table. So only what defines the inherent structure of your data set is what you're going to feed to the model. And maybe I would have missed to call it out, but this, like whatever I've explained, the architecture is specific for that data set. It's like if you have like 10 different data sets, right? Each data set has its own architecture, and that's determined at the time of the trialing process. So it does like based on the number of layers and whatever we define, the activation functions that define, we conduct hundreds of trials and we feed into the model and then pick the right architecture that suits for that data set, that specific data set, instead of using the same architecture for all the data sets in the data lake.
Great presentation, thank you very much. So I got 2 questions. So when you're doing the inference, you're actually running inference on each row of the data, right?
Yes. And
then how do you handle like time series if that is part of the data set? Because then there might be dependencies that should be captured by multiple rows of data.
Yes. So one thing, so the first thing to call out here is we are not using this autoencoders for doing an absolute value prediction. For example, if you're trying to predict when is this incident created, the exact date, that's not what we're trying to solve here. We are trying to calculate, what we're trying to see is the relative value, okay? If the inherent structure or the input data is in accordance to that structure, it should be able to predict some value, some date field in that column when it able to reconstruct the record in the outside, right? So when it comes to time series, in our case, like we're considering it as just like a string and using an label encoding to encode the data, and we're feeding it to the model. Because we're not trying to predict the exact absolute date value, we are fine with the relative value. As long as it can pick some date from the existing encoded values and say that this record structure in accordance to that, that is good enough. Because since we're not doing an absolute value prediction. Does that answer your question or?
So next question, I'm over here. It seems like this is a really cool solution, but it feels like there's a scale problem here with the number of data sets, right? Because you're basically making a custom architecture for each data set, which is probably super time consuming. Are you trying to find a way to standardize this in some way where, maybe common features about certain data sets can have the same architecture or some sort of way of scaling this? Or is it just the type of thing where you only do this on really your most important data assets?
As I said, like as of now, we have implemented this only for 200 data sets. That's why you can see the number of sets. And the best use case that fits in our data lake is with the file extracting process, right? So where it works better in that space. But coming to your question, yes, it does take time based on the number of input records that you're inputting to the model for processing. But if you can cut down, that's why the first key thing here is identifying the good quality data set and cutting down your number of features. Bring it down to what is actually needed for that data set, like which defines your inherent structure. If you get down to that, it will drastically reduce your.
And one other thing with autoencoders is it's not like the traditional large language models or anything. In this case, I can explain it to you offline, but it is once you train that, only the model weights are stored in the backend, and we are able to store them in a simple MySQL backend, and the skeleton is generic. So at the time of running, you can actually load the model on the fly for any specific data set. So even if you have 200 data sets, right? They are basically 200 records in your MySQL database, and the skeleton is generic. And you load it on the fly, and you infer it, and then offload it. It's not like huge. It's pretty straight.
And we don't have to keep that model up and running all the time.